Good afternoon, students. Uh, so today we are discussing artificial neural networks. So we will start with the overall inspiration behind, these models of machine learning. Neural networks are the mathematical models which actually represent the parallel machines, and they actually represent massively parallelism or massively parallel machines. We have the inspiration from the biological neurons, which we will pick up for a very short and see why we have and what is that inspiration behind. So, and more emphasis will be on the overall design of the neural networks for given classification problems or given regression problems. So, these are the models inspired by the working of human nervous system. It has a number of neurons performing the task similar to human neuron. Each neuron triggers the received input according to the weight. We will talk about the weight in a slightly different context than what we were discussing earlier while we discussed the classification problem and its solution. Of course, the term weight represents a kind of coefficient or a kind of percentage of that information that we want to use for triggering the output. So a neural network captures the environment it has to learn in terms of the weights. So you have already seen that learning takes place on the basis of the training data. What the system learns from the training data is captured in terms of these weights. You saw earlier the learning required us to design a decision boundary, and the decision boundary was defined by some parameters like slope and intercept. Similarly, we can say that here we are capturing the environment in the form of some values which we name as weights. So, what is brain computer? The name itself is the kind of illustration that brain processes a large number of information data. Human brain contains a massively interconnected net of about 10 billion neurons. The biological neuron is the simple arithmetic computing element. So what it works on the basis of is the kind of total weighted sum of the information received by each neuron in the humans. Some artistic perception of the neurons in human brain is like this, which I do not have a way to verify, but definitely medical scientists would have seen it through their different computations, different equations, or through different types of microscopic views, which I do not have any expertise in. I'm just taking it as an artist perception. Here you can see that there is one part of this entire nervous system which is accumulating several inputs from different directions, or it is actually passing certain information to the other neurons through its connections, which are called as synapses. Similar entities are large in number. There could be a different overall arrangement of these type of cell bodies of neurons, which are connected through different kinds of layouts between them, right? So you can visualize this to be collecting information from different neurons. You may take one example of doing two tasks at a time. I can take talking and walking. When you're talking on phone and suppose you're walking, definitely you have to focus on what you have to respond to the other person on the phone, and also at the same time you also have to identify if there is any risk in the front of you on the road. So sometimes if your focus is more towards talking, then it may so happen that you are not giving any attention to the view out, there in front of you, and you may fall or you may hit some vehicle, or there could be some accident, right? So it all depends on what your neurons are triggering to the brain, right? And what is being processed by the brain to trigger the control signals. Had there been better control signals through this information, you would have saved yourself from falling, or you would have saved yourself from hitting the vehicle. So more focus is actually a kind of training to these neurons to save you from falling, so that you can have a complete balance between walk and talk. And if you cannot, and rather it is not advisable that you should talk while you are walking on the road. It is because your attention may change the focus and then you may get hurt. So what is this neuron triggering to the brain is the weighted sum of information that it has received from all around. So probably through your eyes you receive the signal that there is no vehicle on the road. Through your ears you process some signal and you give that information that there is no vehicle on the road to this neuron, which it triggered to the brain based on this weighted sum of information, and then you continue talking. But probably the vehicle came all of a sudden, and your eyes did not proceed with that kind of processing, and the correct message could not be transferred to the brain to save you from getting hit by the vehicle. So several things keep coming from different neurons through different ways. This is somehow you can relate with the kind of sensors that we use in the intelligent systems. We humans have eyes, ears, touch, and several other ways to input the information about the environment we are living in. So if the inputs are sufficiently used to train your brain, you are less likely to get hit. But if you have not trained your system very well, it may so happen that there is a problem. So this was just a real life example which I am trying to relate to the kind of triggering of the information to the brain. It is a weighted sum, and the weights come in the real life scenario by your training, by your practice. If you're cautiously walking on the road, definitely your brain is trained to walk cautiously. And that actually is being taken and received by the neurons and then passed to the brain. So training is very important, and we take inspiration from human neurons in one specific form, and that is the weighted sum of information. We actually take the inspiration of human neurons just in the case of weighted sum. And definitely other things which we use in artificial neural networks are all different from humans, right? So you can see that there is a small structure which I am not going into much detail. If you are interested, you can see these details yourself, because I'm not at all good in the biology, but I just thought of bringing this figure to you so that you can understand some correlation between human neurons and the artificial neural network. So the joints are known as synapses. The neuron cell body takes the input from all other neurons and it passes to the other neurons. The other neuron also is not only taking the input from this neuron, it is also taking input from different other neurons, which you will see that this also is a kind of inspiration for us when we talk about the learning machines based on neural network. Okay. So the biological neurons, they have a body cell which is large, round, central body in which almost all the logical functions of the neurons are realized. And then there is this axon, which is the output. It is a nerve fiber right, attached to the soma, which can serve as a final output channel of the neuron. An axon is usually highly balanced. So definitely you may have to consult a biology expert or a neurosurgeon who knows different things about the neural architecture in the human brain. But for us, all these things are used as simple inspirations for us to design the mathematical model. So the dendroids inputs, they represent a highly branching tree of fibers. These long, irregularly shaped nerve fibers are attached to the soma. Then synapses are specialized contacts on a neuron, which are the terminating points for the axons from other neurons. Okay, so a neuron is a nerve cell, and it is a basic building block of human nervous system. Neurons transmit information throughout the body. Okay, these neurons transmit the information in their chemical and electrical form. Each neuron contains a nucleus that has genetic structure. So the connection between cells, this is known as synapses. The connections are known as synapses, which we also use for our machine learning algorithms. So for more interest, you can read something on how electrical signals communicate between the neurons. Also, there are neurotransmitters, which are the chemical messengers to transmit information from one to another neuron. So the major neurotransmitters are as follows. Acetylcholine. These are all the technical terms which definitely people from neuroscience would be very, very comfortable with. These neurotransmitters, they are associated with memory, muscle contractions, and learning. A lack of this particular chemical in the brain is associated with Alzheimer's disease. There is another kind of chemical which is called as endorphin. This is associated with emotions and pain perception. The body releases endorphins in response to fear or trauma. You can understand by reading this real need to understand and be inspired by human nervous system, which has a good, very, very good learning base. And this motivates us to design the artificial neural networks better. And there is another chemical called dopamine. This is associated with thought and pleasurable feelings. Parkinson's disease is one illness associated with deficits of dopamine, while there is another disease called as schizophrenia. It is strongly linked to excessive amount of this chemical messenger. This kind of chemical between the two neurons creates certain diseases. That means the training and the classification and the recognition, etc., are affected by these kinds of chemicals. Of course, the chemicals in their own sense are not directly used for the motivation for us, but the neural network as a whole inspires us. The summation process, it is very important. Each neuron is connected with numerous other neurons, receiving numerous impulses from them. Summation is the adding together of these impulses at the axon hillock. If the neuron only gets excitatory impulses, it will also generate an action potential, right? So here we are talking only about the human neurons. If the neuron gets as many inhibitory or excitatory impulses, the inhibition cancels out the excitation and nerve impulse will stop there. Summation takes place at the axon hillock. Spatial summation means several firings on different places of the neuron that in themselves are not strong enough to cause a neuron to fire. So basic crux of this entire discussion is that we have to have some response at a neuron to get fired for an output, which is the desired output, and it is the resultant of the training. So, however, if they fire simultaneously, their combined effects will cause an action potential. So, nothing to worry about. Every biological inspiration may not be directly used, right? So, let us see how we just motivate ourselves to understand that there is a neural network system in human brain, and humans recognize different objects or faces or situations based on such huge neural network structure inside their brain. As an example, if you have to identify how humans recognize a face, we have the information getting captured through eye. The information passes to the brain via synapses. There are about 1,000 billion neurons in the human body. The information is passed through these neurons in the brain, right? The brain trains itself with the prominent and discriminatory features of an individual. Okay. You also learned in the previous discussions the distinguishing features which are important for understanding of the object. So whenever the person sees the same face again, a query is automatically generated in the brain. Okay, so the brain answers the query who that person is on the basis of training already done, right? So the neurons process such information. Of course, here the feature extraction is also done by human brain, which you can also do by artificial neural networks. So when we talk about artificial neural networks, we understand that these are the mathematical models to solve problems whose algorithmic solutions are difficult to be designed, or algorithmic solutions do not even exist. That you've already seen in the machine learning discussion, machine learning algorithms discussion, that there is nothing like traditional algorithm which we can use to solve certain problems, and these type of problems can only be solved by examples, and the system is made to learn such examples and their outputs. So the technology of neural network is more useful when the learning has to take place on the basis of observations. So these models are based on the human neural system. Okay, it collects input through various interconnection links, which we call as synapses, and they pass the weighted information to the neurons, as we have seen in the previous slides also. So basically, a mathematical neuron is a processing unit capable of receiving inputs from single or multiple neurons, and it triggers a desired response. Okay, we will see how these responses are worked out with the given data, how we calculate the weights, and how we train our neural networks. Each neuron has an associated activation function which takes as input the weighted sum of the inputs coming to the neuron, and then triggers a response depending on the associated threshold. We will see what this threshold should be, what the weights should be, how the weighted sum should be viewed as, and how we can see that the weights are selected in such a way that they produce the desired output of the training set. Okay. Yeah, so I just found some chat questions. Yeah, schizophrenia, maybe because of dopamine. Definitely, I'm not the expert to tell, but I picked up certain things from the Google. Probably some doctor can also confirm this. I never tried to confirm. I'm just trying to share this significance of the, electrochemical signals in the brain which pass from one neuron to another, right? So, Yeah, neural network models are also called forecasting methods because they help us in the predictions. So neural network models help us in training themselves and be able to learn from the given training data and then be able to respond in the new situations. Okay. So yeah, so now we have this very simple perceptron model here. So you can see, you can recall that x0 to xm, these values we had been seeing earlier in the form of the feature vector. You can recall that feature vector is a collection of those significant discriminative features which define an object uniquely. And these features, when plotted in a n-dimensional or m plus 1 dimensional space, would get plotted as a point. And this point is a kind of representative of the given object whose y value is part of your training data. The y value which is the part of your training data. So what you have on the left hand side is your x, and what you have on the right hand side of this is your y. And what you have in between is your processor. Basically, the processor is the one which takes as input the weighted sum of the input features and produces the expected output for the training data. So through this x and y pair, we are able to compute the weights. The weights are here, which are actually associated with each synapse. I can say that each input is connected through a neuron, which we may call as input neurons, with the processing neuron, right? So there is an input neuron where you are, inputting the feature, and then there is a processing neuron which is picking up that feature, right? So one could be received through the eyes, another could be received through the ears, the third could be received through the touch, and so on. Or maybe all are there which you receive through your eyes, or equivalently the camera. So these different inputs coming in the form of x0, x1, x2, x3, etc., defining that particular instance or object would get processed by the processing unit Vk and would be able to produce the output y1. Yeah. So processing unit is a kind of code written to decide. You can say that it is, but there is an underlying procedure. As you can recall that the learning algorithms or the machine learning programs are not traditional in their way of working. Machine learning programs take as input the input training feature vectors and take also as input the training output. In turn, it produces a program. Are you able to recall this definition? We had discussed it long back that the machine learning takes as input the input feature vector plus the output, and it produces the program, right? So I just write it here so that you are able to recall this figure. So input and output is taken as the data for it, and it produces a program. And you can also recall that program is nothing but those weights. The weights are defining what type of program we want, right? So weights are basically the program. So program, you can say, is nothing but the weights, because these weights only will decide whether you are getting the output correctly or not, right? So how do we get these weights? One method is that you can randomly allocate some values to these. So randomly select the values of weights. Okay. Had these been a very small number of weights, say 5 or 6, you could have still tried to guess the values, and you would probably come up with some kind of combination of weights which gives you the least error in terms of classification or in terms of regression. But if these weights are large enough, or the number of samples that you have to train with is very large, then humans will have the limitation of deciding the values of these weights. Then we would expect our program itself to be able to learn from the given data. This learning happens because now it has a clear guideline of selecting those weights which produce the minimum error. Least squared error is the principle behind this learning, right? So then we move ahead and see a small neural network model. I would say that if this is my neuron where I have used the sigma as a symbol for accumulating the entire input in its weighted sum form. So suppose this neuron which takes its input an x1, which is connected through this synapse, and this synapse has a synaptic weight as W1, would contribute as W1x1 to the processing neuron here. And then the second neuron taking input as x2 through its synapse with the weight W2 would contribute as W2x2. So in a way you can say that the weighted sum at this processing neuron is summation Wi xi, where I varies from 1 to n, where n is the dimensionality of the feature vector. Then there comes an activation function. Whom should this neuron fire? This will take the weighted sum, apply a function. If this function's overall value is larger than a threshold, then it will trigger an output as 1. Or if its value or the weighted sum's value once applied with this function f is lesser than the threshold, then y will output as 0. So basically if we talk about the binary classification in which y can take either 0 or 1, then the function f would be taking a decision to report a y as 1 if the weighted sum's response is larger than t. We call such kind of functions as step functions. Okay. Here we have this simple logical AND. This is a logic which humans have, right? And the logic says that if you have two signals coming with 0 values, the AND logic will convert it to 0. If you have one signal coming with 1 and the other coming with 0, the AND logic will convert it to 0. Similarly, with 1 and 0, you have a 0. With 1 and 1, you have a 1. That is what is the AND logic. I'm not talking about a logical AND gate somewhere. It is not at all a concern to implement it in the hardware right now. I'm only simply talking about the logic. And this logic is coming from the human brain, which we want our system to handle and be able to understand this logic later even. So I can even expect my system to understand a new signal like 0.9 and 0.85, right? 0.85 as x1 and x2 to be identified as 1. Similarly, I may expect this learned system to understand this value 0.001 and 0.98 to understand this to be a value 0. Because then we would say that anything that is close to 0 and anything close to 1 should map to a 0 class. It is a binary classification where x1 and x2 is representing the y value. So I can say that this is the y value, okay, and x1 and x2 are representing the feature vectors. So yes, I am taking this question from Venkat. How is this different from regression? classification because there also we train model and get outputs. Here also seems to be like that. So exactly, we are working towards building new types of models to do the same activities, which we did earlier through the classification boundaries or designing a line that fits, right, through regression. Here we are wanting a neural network system to understand the weights through the training data and be able to classify using this machine, right? Earlier, the learning machine was different. We were actually trying to plot the entire set of training data into n-dimensional space and then trying to find out the classification boundaries. As long as that is a simple straight line or a straight plane, life is much simpler for the for the people who classify. But when it comes to defining a surface in the n-dimensional space and be able to identify their belongingness to the data, it really becomes very, very difficult. So neural networks, they themselves represent the classification boundaries internally, and then the classification is done without even plotting the data into n-dimensional space, right? So here we take some activation functions. The activation function is defined as f of n equals 1, right? Whenever this n, that is the weighted sum that we will be picking up later, n is equal to summation wixi. If that summation is greater than 1, then I would say that the output is 1. So f of n is nothing but the output. Otherwise, it is 0. Okay. We will see the magic of this neural network, that it will be even able to classify this type of unseen data such as 0.9, 0.85 or 0.01, 0.98. What it has seen so far is only these 4 feature vectors and their corresponding outputs. So even though it has not seen 0.9, 0.85 type of data, it will be able to still classify it to the best of human understanding, right? Here, let us say we have this neuron. Okay, you have already seen that structure. This is a neuron, and if there are 2 different synaptic, connections coming from 2 different input neurons, I can call these neurons taking input for x1 and x2, and this is the processing neuron. Okay, this processing neuron takes as input x1 w1, okay, plus x2 w2. Okay, so let us call this this expression to be defined by n. So we do not know w1 and w2, but we know x1 and x2 for one sample training data. x1 and x2 being 0, we know that its output should be y equal to 0. So what do we want? We want something as f of n to be equal to 0, right? We want this f of n to be equal to 0. What is this n going to be? N is going to be the sum of w1 x1 plus w2 x2. Since x1 and x2 both are 0, the value of n is anyhow 0 irrespective of any weight. You can keep any weight, any intercept or slope, but you are not able to recognize that intercept and slope in this model. We will try to relate it later. So let me take these x1 and x2 being 0. We take w1 as anything or w2 as anything, but this entire weighted sum is coming out to be 0. So f of n is 0, whatever be the threshold. So suppose my threshold was, let us say, 1, right? Then f of 0 is actually equal to 0 because it is less than the threshold as per the previous definition. So for case 1, that when x1 is 0 and x2 is 0, we do not have to worry. It will work for any pair of weight parameters. But which weights should we select? We cannot take different weights to different data. The same set of weights will be there for all data sets, right? W1, W2. Which W1, W2 should give us the minimum classification error? If I'm having x1 as 0 and x2 as 1, which expression am I getting? N is equal to W2 using this first expression. N is equal to W2. What is this output we want for case 2? That is x1 equals 0 and x2 equals 1. The output that we expect through our training data is equal to 0. That means I want in any sense W2 to be less than the threshold so that I can get Fn as 0. So what if I'm taking W2 equals 0.6? If I'm taking W2 as 0.6, you will get N equals 0.6. That means f of n will be equal to 0, and that is what we expect. So any W2 which is less than 1 will work for us in the second case. Then comes the third case. x1 equals 1 and x2 equals 0. In that case, what I'm getting as the weighted sum is actually equivalent to W1. And this W1 should be selected in such a way that f of n should be equal to 0. Threshold has been fixed in the very first instance, right? So we can take W1 as anything. We can take W1 as 0.4, or we can take W1 as 0.5, right? Or even 0.6, because anything will be lesser than the threshold that we have already fixed as 1. So long everything is correct, 0.6, 0.5, these should be the weights. And at least for these three cases, we will not get any classification error. Will the same set of weights and the threshold would work for the fourth case, that is when x1 is 1 and x2 is 1. In that case, the expression for n is W1 plus W2. Had we selected W2 as 0.6 and W1 as 0.5, we would have got the value of n as 1.1, right? And since this n being 1.1 is greater than the threshold of 1, we can say that f of n is equal to 1 based on the function that we had defined as the activation function. So even taking W1 and W2 as 0.5 and 0.6, we are still able to get the fourth case not fail in its classification. So we are still not getting any error. So entire classification error so far is 0. We are able to understand, we are able to get the optimal weights as 0.5 and 0.6. Now let us look at another situation where I may take a weight of W2 for the second case. I'm taking W2 as 0.4, and you can understand, as long as the case 1 and case 2 are concerned, we are still able to get f of n as equal to 0 because n is making up as 0.4, which is less than 1, the threshold, and still we are able to get f of n as 0. That means this is the predicted output. F of n is actually the predicted output. Okay. And what is the correct output? Actual output is anyhow y equals 0, that we know for 0 and 1, the second case. So that means there is no classification error. The predicted output is 0 and the actual output is also 0. So there is no classification error if we had taken for second case W2 equals 0.4. Now let us come to W1. I'm again sequentially coming from case 1, case 2 to case 3. And now instead of W1 taken as 0.5, let me take W1 equals 0.3. This makes n equals 0.3 and we get f of n as simply 0 because n's value is lesser than 1, which is the threshold. So by this end of the third case, even despite taking W2 as low as 0.4 and W1 as low as 0.3, we do not have any classification error. But as soon as we come to the fourth case, what becomes the value of n with these weights W1 and W2 taken in blue color? This comes out to be W1 plus W2, that is 0.3 plus 0.4, and this also will take me to 0.7, and since this value is less than 1, I will get f of n as 1, f of n as 0, right? Am I right? For the fourth case, with the W1 as 0.3 and W2 as 0.4, are you agreeing that f of n should be 0? Anyone? Yeah, can you respond? In the fourth case, you get with W1 equals 0.3 and W2 equals 0.4 a value of n, the weighted sum, as 0.7, which is less than 1. And then in that case, the predicted output will be 0. While the actual output of this input 1, 1 was actually 1. So basically this leads to a classification error of 25% rather, I would say, right? So out of 4 samples, 1 is going wrong with such kind of weight selection. 0.4, 0.3, or let us say W1, W2, you are taking 0.3, 0.4, that is giving you a classification error of 25%. But a selection of W1 and W2 as 0.5 and 0.6 were not giving you any error. Yes. So, Prakash, the optimal weights selection is a technique. We cannot keep guessing on these combinations. We have techniques such as gradient descent method. We can also find approximate optimal weight in very less time using some evolutionary algorithms. It all depends on their parameters as well, how quickly you will get the optimal weights. But there are deterministic algorithms which give us optimal weights. But here the need is that you understand that we are posing the classification problem using neural network as a combinatorial problem of weights. The combinatorial problem of weights means we need to find the best combination of weights such that we get the minimum classification error. So now you can see that we are now not just posing classification problem as a combinatorial problem, we are also posing it as a optimization problem, right? Using the neural network, finding such weights makes this classification problem posed as optimization problem, okay? So anything that works good for any optimization can also help us in identifying the best weights. Okay. So with W1 and W2, if I am taking W1 and W2 as 1, 1, what will happen? I am getting N as 2, right? If I am getting N as 2, then also the same activation function will help, right? Here I am getting the output as 1, okay? If I am taking W1 and W2 for all such training data as 1, 1, you will get 0, 1, 1 as the weighted sum. So here there is a slight change in our definition of the function. Can you tell me what it is? the definition that we were using there was f of n equals 0 if n is less than t, and it was taken as 1 otherwise. Here the difference is in its definition of 0. I am here taking n less than or equal to t case as fn equal to 0. Are you getting this point? So there is a slight difference between the weights that we selected in the previous slide and these weights which are selected as 1, 1. So not just the weight, it is also the threshold that matters. Right? So the threshold here is taken as 1, and not just the threshold, it is actually the complete definition of the activation function that matters. With this definition, we are still not getting any classification error, right? So this is all about supervised learning using neural network. Here we know the expected output and we adjust the weight to get the output. And this is the supervised learning process. Learning is in terms of obtaining weights. Okay. The neuron is trained with the input pattern 0, 0, 0, 1, 1, 0, and 1, 1. So as to learn that, the pattern should be named. So you can just see this typo error. You should change it to BE. Named as 0, 0, 0 and 1 respectively. So 0 is the name of the class and 1 is the name of the other class. So once a neuron is trained, it is expected to use its learning to answer any input pattern. Right? Say for example 1, 0. It has already seen this pattern. It has to answer it to be 0. It has to answer that it is 0. And there is no logical operation we are performing anyhow. It is only that the neural network has learned logic without being explicitly told that this is the AND logic. Okay. So here we do the testing. You can understand that 001 and 0.001 and 0.987. It is that signal whose x1 value is 0.001 and x2 value is 0.987. I can say that this is a weak signal, right? Because it is not fully 1 or 0, it is a weak signal. But are we able to create a learning machine which also understands these weak signals and is able to classify their output, performing the AND logic? Let us see what it gives us with the weights 1, 1. If I am taking weights as 1, 1, the weighted sum is 0.001 into 1 plus 0.987 into 1. And it makes it 0.988, right? Based on the definition of our activation function discussed in this slide, f of n will be equal to 1 if n is strictly greater than the threshold. Is it so? Or is it the otherwise? F of n is 0 if n is less than or equal to t. If I am taking t as 1 in the training process, then t remains same in the testing process also. And then t being 1 is larger than 0.988, which is the weighted sum. So f of n is equal to 0. So even an unseen pattern is also recognized correctly, right? Another input you take 0.876, our unseen x1, x2. This is also considered to be a kind of weak signal because it is not 1, 1. But still, your neural network is able to recognize such kind of sample signal as a 1 class, right? So since its weighted sum comes out to be 1.8 and it is larger than the threshold, then your output, the predicted output is 1, while it also should be equal to 1 as its actual output. So even testing errors are very less. Similar samples, if you use 100 in number and you find out that the corresponding weighted sum is appropriately used to compute Fn, you will find that Fn and the actual output Y do not differ much for many samples. If out of 100 you are able to classify these samples 97 in number, you will be able to say that you have classified 97% correctly. That is just one definition of accuracy. You could go for different other kinds of definitions and performance metrics like confusion matrix or ROC curve, etc. So even if you have 1.009, which is even stronger a signal, or it could be a spike, 1.1, is that also being classified as 1 correctly? It is, because now we are getting the weighted sum as 2.1. And since it is greater than the threshold, I am getting the predicted output as 1, which is expected. So here also there is no error. You can see how a very simple single neuron model helps us to make the system learn a logic which is a simple AND logic. Okay, so can you classify the signal 0.05 and 0.001? Can I expect some answers from you? I am taking f of n as equal to 1 if n is strictly greater than threshold and is equal to 0 otherwise. Rather, I should say it is greater than, right? So I would change this. So f of n, if it is strictly greater than t, then we say that, it is equal to 1 if n is strictly greater than t and is 0 otherwise. Otherwise means it is n less than or equal to t. Okay. So can you classify? How did you approach this? Yeah, 0 is the answer. How did you get? Yeah, 0 is the answer. So what are you computing now? The weighted sum. So what is the weighted sum? You can find out n, the weighted sum, as W1 x1 plus W2 x2. I am assuming that I am taking W1 equals 1 and W2 equals 1. Based on the training that we have done. In the training, we have received 0 training error. Based on that, I am taking the same weights to use for testing. So with these weights and x1 and x2 being 0.05, okay, x1 and x2 being 0.05 and 0.001, what do we get as n? N is equal to 1 into 0.05 plus 1 into 0.001, and this comes out to be 0.05 plus 0.001, which is equal to 0.051. And since this is less than 1, the threshold, I am taking threshold as equal to 1, right? So then this n is coming out to be lesser than the threshold. That means f of n is equal to 0 in this case. So this data is actually totally unseen, you can see. This is where you can rely on the neural network that it has the capability to even classify the unseen input, provided we have the best weights to train it. Is this comfortable? Fine. So f of n is the predicted output. Had you used a validation set, you would have also had a value of the actual output y given as 0, because we know that these two are the two equivalents of signals which are close to 0, and their logical and output should be 0. Their logical and applied between them should be 0. So y being a actual output, right? You can see that the this neural network model has given you prediction exactly same as the actual output. So there is no error even of the testing, right? With this simple model, I would ask you to do a simulation of OR logic, right? OR logic would require you to have x1 and x2 being defined and their corresponding y. Yes, so I will come to that question, Venkat. So I'm trying to give you this problem for generating a neural network with one perceptron model, one simple neuron, which mimics OR logic. I'm not saying that there is any hardware, representing this OR function, or I'm not even having a if and else condition, such as telling the system that if x1 equal to 0 and x2 equal to 1, then y y predicted is 1 or 0. I'm not saying that. This is not algorithmic. This is something which is learned through examples. The examples will be 0 and 0 giving you a 0. Okay. Sorry. 0 and 0 giving you a 0. 0 and 1 giving you a 1. Okay. And 1 and 0 giving you a 1. And 1 and 1 giving you a 1. So the weights will differ. When you had seen these in the example earlier, you had the outputs, the actual outputs as these. The actual outputs were 0, 0, 0, 1 for these set of inputs. Now you have, I'm referring to slide 17 right now to show you AND output, okay, as 0, 0, 0, 1. Now in the case of OR, I'm coming to slide 25 now, and showing you that the outputs are different, 0, 1, 1, 1. What will be your weights if I'm taking the same input and output conditions? So this is input neuron x1, x2, and the output neuron is, the processing neuron is this. Okay, so I'm saying that this is x1, this is x2, and this is the summation. So I'm representing summation as sum, or you can find out what is f of n here. Okay, so what is n that you're finding out here, and then these two are inputting to the neuron here, these two are inputting to the neuron here, and there is one output y. So instead of taking this y, you are able to compute this value of p of or f of n, right? So I'm asking a question: what should be W1 and W2? Okay. What is your activation function? Okay. And what is the threshold? T. Okay. So that your training error is 0. Okay. Have you worked out? Okay. So one suggestion from Anirudh is that we can use the same weights and change the threshold. Yeah, W1 we can take as 1 and W2 as 1. but the threshold we will have to change. Making change in the threshold will help us getting more ones, right? So the function that you are describing is f of n equals 1 if n is strictly greater than 1.5. Can we not add equal to condition here? And it should be equal to 0 if n is less than or equal to, let us make it this way, less than equal to 1.5. So if you had weights as W1 and W2, then what will be your f of n? F of n for the first sample would be 0 multiplied by 1 plus 0 multiplied by 1. That makes n equals 0, and since it is less than 1.5, we have fn as 0. That means the predicted output is same as y1 being 0. The second sample, the training data, 0, 1, with its output y1 as 1. Y1 is only being used for calculating the error. Y1 is nowhere involved in identifying the function value right now. Of course, when we will do the automated weight selection, definitely this y1 is going to give us the error surface, right? But right now, when you are doing manually, this y1 is helping you to identify whether you classified correctly with fn or not. So with 0, 1, the second input training data, you get 0 multiplied by 1 as 0 and 1 multiplied by 1 as 1. So the weighted sum n is coming out to be 1. And since this is less than 1.5, if you're making it 0, would that be fine? No, we want a 1, otherwise it will be simply a 0. What should we do now for 0, 1? It does not work. Is this the same model that you suggested, Anirudh? So, what changes should we make in this? We want the output fn to be 1. And here the weighted sum is actually 1. So, should we reduce the threshold from 1.5 to 0.5, let us say? Will that work? Yeah. So, if I change my threshold from 1.5 to 0.5 and I redefine my function, I am making use of a different color to redefine my function fn, the activation function. F of n is equal to 1, right? If n is greater than 0.5, let us say, and it is equal to 0 otherwise, right? So what will happen? Since now my n value is greater than 0.5 for the second data, okay, second data will give me 0 into 1 plus 1 into 1. That is, now for this second data I am getting n equals 1. Since this is greater than 0.5, I am getting the predicted output f of this n as equal to 1. And this fn being the same as y1 value for the second row, I say that this definition of the activation function helps us. Similarly, the third data 1, 0, that will also give me 1 value of n, and it will turn out to be the predicted output as 1. What about the fourth input? Fourth input is 1 and 1. So the weighted sum will make it equal to 1 star 1, 1 that is x1, and another one is w1 plus 1 into 1 that is w2 x2, and this comes out to be 2, right? Whatever it is, since it is greater than 0.5, then I am getting its predicted output of the fourth data to be equal to 1. So where do we have to save ourselves from, getting into the output as 1 is only for the first row. The first row has to be saved from being predicted as class 1. Okay? Are you understanding this? Yeah? Others? Okay. So I'll come back to this after a small break, and we will then continue with the more complex problems using more neurons, right?